Hi and welcome to this Expert of the Week interview where we get exclusive insights to why it is important that we measure parameters of the atmosphere. I'm very happy to welcome Professor Erland Schelein, who is Director of Research at the European Centre for Medium Range Weather Forecast, ECMWF. Erland, can you tell us a little bit about your background and your current job?
Well, good morning. I have an academic background. I have most of my career at Stockholm University in Sweden. I'm a professor of dynamic meteorology, and my main research areas have been large-scale dynamics and numerical weather prediction. I started my academic studies at Lund University in the mid-1970s, and I was studying mathematics and physics. And I was searching for an application area of physics, and that's how I got into meteorology, which I started to study in Stockholm, and I got a big PhD in Stockholm in 1980. I think meteorology is a both fascinating and practically useful application of basic physics and mathematics. So presently I'm working as Director of Research at ECMWF, the European Centre for Medium Range Weather Forecasts, which is located in Reading, England. And I'm heading a team of scientists that develop methods for numerical weather prediction. One very important aspect of numerical weather prediction is to use satellite data to determine the starting point for the forecasts. And we call this process data assimilation, where we take all the satellite data that we can get and use it to determine the state of the weather at the start of the forecast. We also develop the forecast model, and we use supercomputer resources in order to produce weather forecasts for users all over the world.
So we already got some insights. How would you describe our participants, what the ECMWF is doing in general?
Well, our core mission is to deliver medium-range weather forecasts. That's weather forecasts on the timescale of 2 to 10 days ahead. And we deliver these forecasts to all our member state Met services. We have about 20 member states in Europe, and it's the national meteorological services of these countries who receive our forecasts. And they are a basis for weather forecasting in all our member states. And they're also used at a number of other places around the world. Many of the largest Met services subscribe to our forecasts and use them in their operational services. We are around 280 staff here in Reading. And our biggest piece of technology is a massive supercomputer that we use for the forecast calculations. But actually, most of the computing power we have is used for research, to develop new versions of the forecast model. But at certain times of the day, the computer is fully busy with producing the next medium-range weather forecast.
Wow, that sounds like a very important and especially huge operation. So I guess, based on what you said, that Earth observations play a large role or a strong role in your daily business.
Oh yes, we use them a lot. And we use around 40 million observations per day. And the vast majority of these, they come from satellites.
So you say satellites, but what happened to the classical weather stations everybody has in mind that are on the ground? Did they become obsolete?
No, we still use surface weather stations as well. But of course, surface weather stations are only located in inhabited land areas. And if you look at a map of the world, you see that you have a concentration of surface weather stations over North America, in particular the United States, over Europe and Southeast Asia. But all other parts of the world are actually quite empty in terms of surface observations. So we must have satellite data to complement the conventional surface observation network. However, I must emphasize that having the surface observations as well as the radiosondes or weather balloons is absolutely vital to anchor the satellite data. We know that satellites observe radiative fluxes, and there can be biases in the measurement of these fluxes. And in order to correct for these biases, we must also have the surface as well as the in situ observations from radiosondes to calibrate the whole observing system.
Ah, I see. So it's the combination of satellite observations and ground measurements. Would you say that we have sufficient sensors out there to measure the atmosphere?
Well, even if we have 40 million observations per day, there are still huge gaps in the observing system. One big problem is that we're unable to use all the satellite information we receive. Biases that I mentioned before and accuracy limitations force us to discard quite a lot of the information that we get. A very important part of our system is this quality control of the satellite data, to filter out the satellite data that is not useful for us. But of course, the development work we're doing and the data assimilation, the goal of that is to use more and more of all the satellite data that we have available. And we also prepare ourselves for a lot of new sensors that are going to be flown in space in the coming 5 to 10 years. And when we look at the new sensors that are coming, we are particularly looking forward to a mission called Aeolus, a Doppler wind lidar, which will give us much better wind data than we have today. And actually, one of the basic limitations of our present observing system is the lack of wind data, in particular over the tropics.
Many of us take, for example, weather forecasts for granted, but it appears that a lot of sensing, data collection, processing, interpretation is necessary before we know whether it rains tomorrow or not.
Well, yes, we do take the weather forecast for granted, but if you look historically, let's say 30 years ago, the forecasts were much poorer than they are today. We have seen a marked improvement in the quality of weather forecasts, and there is still scope for further improvement. We say today that we can produce useful forecasts about up to a week ahead. And if we compare to 30 years ago, our 6-day forecasts today are actually as accurate as the 3-day forecasts were about 30 years ago. So this really shows the improvement. And the purpose of the work that we do here is to both develop the models, the prediction models that we use, as well as the data assimilation, to use the observations in a better way. Another use of weather forecast modeling methods is to investigate climate change. First of all, we need a consistent, homogeneous set of an observation record going back in time, and we use our weather prediction models to assimilate all the old data as well to produce what we call reanalysis. And then you can use models of exactly the same type to do climate projections, to find out what happens to the climate of the atmosphere under, for instance, increased concentration of greenhouse gases.
So you already mentioned climate change. I would assume that this requires a much broader pool of data sources, because it's not only the atmosphere. There's a coupling with the oceans, the cryosphere, and other regions. Would it be correct if I say that one needs to get a larger picture of system Earth?
Well, for climate modeling, of course, you need an Earth system model that does not only include the atmosphere, but also has oceans, sea ice, and land surfaces. And then the composition of the atmosphere is really a vital aspect of climate change modeling. But also for medium-range weather prediction, we're actually moving more and more towards Earth system modeling, because we know that also on the shorter timescales, the coupling with the oceans, the coupling with the land surface, and actually also the concentration of greenhouse gases and aerosols do matter also for weather forecasts.
So that sounds really challenging. What would you recommend now, a participant of our course who is now interested in those fields?
Well, I would say that Earth system sciences are at the heart of global change. They are at the heart of understanding climate change, global warming. And in order to understand cause and effect, as well as prepare ourselves for the future climate change challenges, we must enhance our capability to do Earth system modeling and observations. And studying Earth system disciplines, such as meteorology, oceanography, and Earth system observations, will give you a basis for developing a career in this area. But it is also very important to point out that you need to have a background in mathematics, and including numerical methods, and physics as a starting point for your career in Earth system sciences. But I've always found Earth system modeling to be a fascinating application of basic principles in physics and mathematics. You can develop advanced modeling tools and theories that can be compared to the observed reality every day.
So you have heard it. I mean, this sounds really encouraging. So for those participants who are now interested, you can help us sensing planet Earth. And thank you very much, Erland, for this really, really motivating interview and these insights in a top-notch research institute.
Thank you very much.